Welcome, everyone. Today, we're diving into a pretty revolutionary concept in engineering: how to create motion not from rigid joints, but from flexibility itself. Yeah, we're going to look at how bending and stretching, the very things engineers usually try to get rid of, can actually be harnessed to build simpler, cheaper, and way more elegant machines. All right, so here's our game plan for today. First, we'll unpack what motion through flexibility actually means. Then, we'll make the case for compliance, why you should even care. After that, we'll explore the 4 lenses for design, which is basically the engineer's toolkit. And we'll wrap it all up by looking at the synergy of art and science in this field. Let's get started. Okay, section 1, motion through flexibility. So first things first, right? What in the world are we even talking about here? Let's unpack the core idea, the fundamental principle that drives this whole field. So here it is, the big definition. A compliant mechanism is one that gets its motion from, well, from the deflection of its flexible parts. Now, you have to understand, in traditional engineering, deflection is the enemy. It's an error, something you design out. But here, it's the entire point. We're not avoiding it, we're using it. And this isn't some newfangled idea. Think about the simple bow. It stores and releases energy through bending. That very same principle is used in super high-tech modern designs to guide motion with incredible precision. This right here really drives the point home. It's a complete paradigm shift. Think about it. In the traditional world, you assume all your parts are perfectly rigid, and the only place motion happens is at the joints, the pins, the hinges. Any bending, that's a bug, not a feature. But in the compliant world, the structure is the motion. The actual bending and flexing of the material, that's the very thing that makes it work. It's a completely different way of looking at the world of mechanics. And you know what's wild? This supposedly new idea, it's as old as life itself. Nature is the original master of compliant design. I mean, think about it. Biological systems almost never use pins and rotating joints. How does an insect's wing flap with such complex motion? How does an elephant's trunk have that incredible dexterity? That's all motion through flexibility. And this natural blueprint is what inspired some of our greatest inventions. The Wright brothers, for example, they steered their first plane by wing warping, literally bending the wings. A perfect early example of large deflection compliance. Okay, so we've got a handle on what this stuff is. Now for the big question, why? Why is it so powerful? What makes this approach so compelling that engineers would, well, bend the rules of traditional design? Let's make the case for compliance. When you boil it down, there are 3 huge payoffs here. First up, cost and simplicity. If you can make something out of a single piece of material, poof, assembly just vanishes. That saves a ton of time and money. Second, you get a massive boost in performance. No joints rubbing together means no friction, no wear, and no need for lubrication. You also get rid of backlash. You know that little bit of jiggle in a mechanism? Gone. You're left with super precise, perfectly smooth motion. And third, and this is really cool, is miniaturization. You can make things incredibly small on a scale where building a traditional hinge would be impossible. And if you want a perfect picture of what this means in the real world, look no further. On the left, you've got a standard crimping tool. Count the parts. There are dozens of them. Pins, screws, springs, a whole mess of things to assemble. And on the right, the compliant version. It does the exact same job, but it's one single piece. That's it. We're talking about slashing the number of parts by 90% or even more sometimes. The leap in simplicity is just astonishing. Okay, but let's be real. It's not all sunshine and roses. This approach comes with its own set of very real challenges. First, the physics get tricky. The motion and the forces are all tied together. They're coupled. You can't just analyze one without the other, and that makes the math a whole lot harder. And then you really have to know your materials. You got to worry about things like fatigue. Is this part going to snap after I bend it a million times? And you have to think about creep. If I leave a load on it for a year, is it going to slowly sag and lose its shape? These are tough problems to solve. But here's the thing. Even with those challenges, these mechanisms are absolutely everywhere once you know what to look for. Seriously, they're in the simplest things, like that little snap buckle on your backpack. They're at the very heart of high-tech gear, like the tiny accelerometers inside your phone that know which way is up. And they're pushing the boundaries in aerospace, making things like shape-shifting airplane wings a reality. The range is just incredible. So this all begs the question, how do engineers actually design these amazing things? It's not just random trial and error. There's a science to it. We're going to explore the 4 main ways they do it. Think of them as four different lenses, or four key tools in the engineer's toolkit for tackling these problems. First step is a method with a bit of a mouthful of a name, the pseudo-rigid body model. But don't let the name scare you. The idea is brilliant. It's basically a bridge that connects the old way of thinking to this new flexible world. It's a way to make compliant design feel a lot more familiar and accessible. So here's how this clever trick works. It takes a really complex bending problem and simplifies it into something engineers know inside and out, a classic pin joint problem. It basically says, hey, let's just pretend this flexible beam is actually two stiff rods connected by a hinge with a little spring on it. And by doing that, you can suddenly use all the standard, well-understood math to get a surprisingly good answer for how that flexible part is going to behave. It's a really elegant shortcut. All right, our next method is a complete 180. This is where we let the computers do the heavy lifting. It's called topology optimization, and it's like starting with a total blank slate. You basically give the computer a problem. Okay, here's a block of material, here's where I'm going to push on it, here's where it's held down, and this is the motion I want to get. Then you hit go, and the algorithm literally discovers the perfect shape for you. And the process itself is just fascinating to watch. You start with a solid block of material. Then, the software runs thousands of tiny calculations and starts carving away any material that isn't really doing any useful work. It's just like a digital sculptor, intelligently chipping away at a block of stone. And what you're left with at the end is this highly optimized, often very organic-looking structure that is perfectly tuned for its job. Strong where it needs to be strong, and flexible right where it needs to bend. Okay, our third lens, constraint-based design, totally flips the problem on its head. Instead of asking, how do I get the motion I want, you ask, how do I get rid of all the motions I don't want? It's a process of elimination. You start by thinking of all the possible ways an object could move, and then you strategically take away those freedoms until only the exact motion you were aiming for is left. Here's what that looks like. Any object floating in space has 6 basic ways it can move. We call them degrees of freedom. It can slide left, right, forward, back, and up, down, and it can rotate around each of those 3 axes. This method uses really simple, flexible parts, like thin metal blades or wires, to act as constraints. Each little flexure you add blocks one or more of those motions, forcing the object to move along one very specific, very precise path. You are literally sculpting motion by taking away its freedom. But okay, what happens when the geometry gets so complex that our intuition just fails? For those times, we need the heavy artillery. And that brings us to our fourth and final lens, screw theory. This is the most mathematically intense approach, but it's incredibly powerful. It gives us a complete algebraic language to describe literally any motion and any force in 3-dimensional space. At the heart of this are 2 key ideas. First, you have something called a twist. Think of it as a single mathematical object that can describe any possible motion, a simple rotation, a straight line slide, or a corkscrew motion that does both. Then you have a wrench, which is the same idea but for forces. It describes any combination of pushing forces and twisting torques. By using the special math that connects these 2 ideas, engineers get this universal language to solve super complex 3D motion problems with absolute certainty. All right, so we've looked at 4 pretty different design methods, the intuitive ones, the analytical ones. So how does it all fit together? Let's talk about the synergy of art and science and bring this all home. The real magic happens when you realize these methods aren't in competition. They're partners. The ultimate goal is to bridge that gap between a creative idea and a rock-solid analyzed design. So you might start with that geometric lens, using your intuition to sketch out a concept. But then you bring in the algebraic lens, the heavy math of screw theory, to check your work, analyze it with total rigor, and find ways to make it even better. It becomes this powerful cycle, from human creativity to computational power and back again. And that's really the big idea here. By mastering this whole toolkit, we are watching this field transform right before our eyes. It's moving away from being just a clever art form that relies on intuition and trial and error. It is becoming a predictable, systematic, and unbelievably powerful engineering science. So I want to leave you with this final thought. Now that we have these incredible tools, now that we can design complex motion without any of the old building blocks, no joints, no bearings, no pins, what does that actually make possible? When you're no longer limited by the world of rigid parts, what kinds of new machines can we even begin to dream up? From the microscopic all the way up to the astronomical, what's next?